Hi, everyone. Welcome to the last functional group of organic chemistry. Today, we're talking about amines. And yeah, I know there's still Unit 5 yet to cover, but that's an introduction to biochemistry. And biochemistry, in my opinion, is just an application of organic chemistry. We're going to look at some molecules in Unit 5, and we'll just look at functional groups in these biological molecules and point them out and see what they're doing using organic chemistry that we already know. So I think you're going to enjoy Unit 5, especially the bio majors and pre-med students. It's going to make organic chemistry much more relevant. But there's no more functional groups after this one. This is the last one, the amines. Okay, so general routine, whenever we see a functional group, we begin by naming molecules possessing that functional group. So let's get right to it. Let's turn on the pen and talk about common names of the amines, and then we'll talk about the IUPAC standardized naming system for amines. First of all, I'm going to be really generous on naming amines. Amines are one of the oldest known organic functional groups. There are a ton of ways to name these, and they're all accepted by the chemistry community. And so if you don't follow strictly these guidelines and you give a very logical name to the amine, it's probably going to get full credit. But if you're not sure how to name the amines, then follow these guidelines. Okay, here we go. Common names. Typically, the format is, hey, well, let's back up a step. What the heck's an amine? That's a nitrogen possessing 3 single bonds to either a carbon or a hydrogen and has a lone pair. That's a typical amine. Okay, so these single bonds to nitrogen are either going to be attached to a carbon or a hydrogen. And so the common name is just based off of that. Just name these groups and throw them in front of the word amine, right? So if you have a propyl group in front of a nitrogen, that's the only thing, this is propylamine. If you substitute one of these hydrogens with a methyl group, then one group is propyl, the other group's methyl, put them in alphabetical order, and you have methyl propylamine, and so forth. That was a pattern for naming ethers, giving ethers a common name. The one weird thing is that when we named the ethers, we had spaces between methyl, propyl, ether, and for the amines, you don't. I won't take points off of that. Okay, so simply speaking, that's how you do it. Here's a nitrogen. You have to stir this group a little bit to realize, oh, there's a carbon connected to 2 methyls. A carbon connected to 2 methyls. And then you have the NH, and then you have another methyl. Okay, and then so you have these 2 groups connected to nitrogen. Hey, that's an isopropyl group over here. Iso gets, you alphabetize using the I of iso, and then the methyl's an M. So the common name for this molecule is isopropyl methylamine. So in your key concepts here, we have the format for tertiary, secondary, and primary amines. And then as I'm looking at this, I don't remember if we formally discussed how to classify amines, classify nitrogen. So why don't we review that if we did it? Now, or let's go over it for the first time if we never did. Okay, it's pretty straightforward. You just count the number of carbons directly attached to the nitrogen atom. And so I found this off the internet. Great place to find some resources, so I didn't have to draw all this. You're not counting the number of carbons attached. Sorry, they're not the number of carbons in a chain. It's all about looking at the bonds to the nitrogen, see how many bonds have a carbon at the other side. All right, so this is primary. Why is this circle over here? Should have been here. Okay, you gotta be a little careful stealing stuff off the internet. Glad I caught it now. Okay, when you stare at this nitrogen and say, hey, nitrogen, what degree are you? Nitrogen has 3 arms, 3 bonds, and a lone pair, and says, okay, on one arm, I'm holding on to hydrogen. This arm, I'm attached to a carbon. This arm, I'm attached to a second carbon. Hey, I got 2 carbons, I must be secondary. Same is true for this one. It says, yep, there's a carbon, a carbon, a carbon. We're tertiary. Turns out, you might remember from the SN2 lecture last semester, amines are actually good nucleophiles. SN2, strong bases are good nucleophiles, and SN2, sulfur nitrogen also. SN2, sulfur nitrogen also. Okay, and it turns out nitrogen can use its lone pair to do an SN2 reaction and add a 4th alkyl group. When that happens, nitrogen takes on a formal +1 charge. It's making 4 bonds instead of its normal 3. And then if you classify the nitrogen, hey, nitrogen now has 4 arms, 4 bonds, and they're connecting the 4 carbons. That makes it a quaternary. You know, you got primary, secondary, tertiary, and quaternary carbon. Well, here's a case where you have a quaternary amine or quaternary nitrogen. You can also call it an ammonium ion, an ammonium salt rather, and that's a reference back over here. Remember in Gen Chem, ammonia, you could add acid to H+. What's my problem here? And you can create the ammonium ion, nitrogen with 4 bonds to hydrogen and a formal +1 charge, the ammonium ion. So this is an ammonium salt, even though nitrogen is not directly attached to hydrogen, still 4 bonds to carbon. Sorry, 4 bonds to nitrogen, making it an ammonium type of system. Enough said, let's see some examples. Hey, and we reference biology, so found some biological examples here. Cool. Poison hemlock, yikes. This is the active ingredient in that naturally occurring plant. What degree is this nitrogen? Or how do you classify this amine? You talk to the nitrogen, and there's a bond here to 1 carbon, bond here to a second carbon, and that's it. This is a secondary amine. How about this one? Well, nitrogen has 2 bonds of hydrogen, 1 bond to nitrogen, that's primary. I guess you call this an amine? Well, Dennis, why are you questioning that? There's 3 single bonds, isn't that what you said an amine was? And I say, yeah, that's true. So following the classification, nitrogen, you're connected to 1 carbon here, second one there, that's secondary amine. But back in unit 1, we talked about the lone pair can count towards a Huckel number. So this nitrogen is part of an aromatic ring, right? It's got a ring. Is it flat? Yeah, as long as the nitrogen rehybridizes sp2, this would be planar. So there is a ring. It's planar. Does it have extended conjugation? Yeah. If nitrogen rehybridizes sp2, the lone pair goes into the p orbital. And then these carbons have their p orbital being used to make the pi bonds. And then finally, the fourth criterion, does it have a Huckel number? Yeah, 1 pi bond, 2 pi bonds, lone pair gives you 6 pi electrons. It's aromatic. So this is an aromatic nitrogen. It's still secondary. Ooh, and then stealing from the internet again, here's a biological example of a quaternary nitrogen, an ammonium salt. Cool. Nitrogen, you have to count it up. There's 3 methyl groups on it, and then the nitrogen atom's also connected to the rest of the molecule. Nicotine from tobacco. This nitrogen, what degree is that? Well, look at the bonds. There's 1, 2, 3 carbons. That's a tertiary nitrogen. If I want to classify the nitrogen atom, I would say, well, there's 2 carbons attached. I would classify the secondary, but it's not an amine, right? No way. It's part of an aromatic ring, but more importantly, the nitrogen is making a double bond. If anything, that would make it an imine. Definitely not an amine. Anyways, if you had to classify the nitrogen, I would classify it as secondary. But it's not an amine, so we're not really going to classify it if we're classifying amines. Got to be a little tricky, right? Let's do a little compare and contrast. There's different rules for different functional groups. If I say, hey, classify these alcohols, you would say, oh, well, I remember oxygen is shy. So you talk to oxygen and say, hey, how many carbons are you attached to? And it kind of looks away from you and doesn't talk to you. And so the carbon that's attached to says, oh yeah, oxygen's shy. Let's see. But I'm the carbon. What degree am I? I'm attached to 1 carbon, 2 carbon, 3. I'm a tertiary carbon. Oh yeah, so this makes the alcohol group a tertiary alcohol. What degree is this alcohol? How do you classify this alcohol? You go to the attached carbon, classify it, it's secondary. How about this alcohol? Oh, you talk to the carbon. This carbon is only connected to 1 carbon. It's a primary alcohol. Primary carbon, primary alcohol. Then you classify these nitrogens, these amines, and nitrogen's not shy. It speaks right up. Hey, nitrogen, what degree are you? Oh, I'm attached to 1 carbon. I'm a primary amine. Hey, nitrogen, what degree are you? I'm attached to 1 carbon. I'm also a primary. Hey, buddy, how you doing? We're twins. We don't look like twins. Yeah, we're fraternal twins. Whatever. Hey, nitrogen, what degree are you? I'm attached to 1 carbon. I'm primary. Okay, so we have 3 examples of primary amines in very different types of alcohols. If you change the alcohol to a halide, same pattern. The halides are shy. Just remember it's different for nitrogen. Yeah. Students then will pick up on other patterns. They'll say, oh, okay, when nitrogen possesses 2 H's, it must be primary. I'm thinking, well, what do you do if there's 1 H? Well, if there's 1 H, do we have an example of a secondary hydrogen? Yeah, right here. If nitrogen has 1 H, nitrogen has 1 H. Okay, it seems to be working. Well, what happens if there's no H's? This one didn't have H. It must be tertiary. How about this nitrogen? It doesn't have a hydrogen. It must be tertiary. No, it's positively charged. Okay, it's quaternary. What if you add this molecule to a low acid? Well, amines are bases. The lone pair can pick up the H. And the product is going to look like this. It started with 1 H, the lone pair will pick up a second one. It's positively charged. So now what degree is this nitrogen? Oh, it's got a plus, it's quaternary. No, this nitrogen is connected to 2 carbons. It is still secondary. Oh, but it has 2 H's. Doesn't 2 H's mean primary? Ooh, so be a little careful with that shortcut. It doesn't always work. Counting hydrogens is helpful, but it's not going to always give you the right answer. The proper way to do it is how many attached carbons are there? This nitrogen has 2 attached carbons. It's secondary. Cool. All right. Enough about degrees. How about we name them? Sure. All right. So this, here has its primary. Okay. So the name of this group, that's a tert-butyl group or T-butyl. This is T-butylamine. This primary amine has 1 attached group that has 4 carbons. It's also a butyl group, but this is a secondary carbon. Yeah, this is the sec-butyl amine. And I guess we could have written out tert-butylamine. Your choice. S-butylamine works too. Hey, what's this one? This is simply a propyl group. I think I wanted it butyl. It's butyl now. If it's just a normal chain, this could be the N-butylamine. You could also name it butylamine. And it should be understood that that defaults to the straight chain, nitrogens at the end of chain of 4. Okay, let me double check my notes. Did we cover all the common names? I think we did. Let's go to IUPAC Names. Double check up here. Did I miss anything? No, we covered all those examples. Okay, IUPAC names came in here and said, okay, I like the common names, so let's adapt those. Go ahead and keep using that amine as a suffix anytime that means the highest ranked functional group. So amines don't contain an oxygen. Remember the general pattern for ranking functional groups? More oxygens, more pi bonds, more important. Okay, so you'll just have to remember that nitrogen is higher than alkanes, alkenes, alkynes. It's more powerful, more important than carbon, I guess, in terms of ranking the functional groups. But it's just under oxygen. So if you have an oxygen and a nitrogen in a molecule, the alcohol wins, the oxygen wins. There's an exception to that, the ether group. Ether loses every time the amine would win. Is this going to be nameable? No, let's not name this. You're not going to see that. That would take a complicated name. So no, let's just edit that out. I'm not going to put that in the test. That's why it's not here in the key concepts. Stay within the box, Dennis. Okay, let's look at IUPAC names, right? So there's a couple of cases we need to consider. Primary is the best or the easiest to do. So go back to this one. The common name was butylamine. That was a common name. Full credit on the exam if I ask you to name that. Someone else might want to use the IUPAC name. So find the longest chain with the most important function group. It's chain of 4, that's butane. Add the suffix. So you drop the E and add amine. So this is butanamine. Step 3 is the number of chain, closest to the most important group. Here's carbon 1, 2, 3, 4. So you put a 1 out there, or you put the 1 right next to the suffix. So be a little careful here. If you said butanamine without a number, I know it looks pretty similar to butylamine, but unfortunately butanamine without a number won't give you full credit, because IUPAC name for this is also butanamine. It's just that the amine group's on carbon 2 of the parent. Okay, so a lot of students, including and myself, maybe I'm still a student of organic chemistry. I think of myself as that. I'm still learning. We prefer the common names. Kind of easier to go. And this one would just be the sec butyl amine. Okay, so primary amines are the easiest to name. Whether it's by IUPAC, well, it's best by common names. Unless if that chain gets a little too weird. Okay. If it's not the highest rank, use amino. We're not ready for that just yet. Oh, if you're not primary, so these examples on the page right now, these 2 that I hand wrote, they're primary, right? Talk to nitrogen. Hey, nitrogen, how many carbons you attached to? 1. Hey, nitrogen, how many carbons you attached to? 1. Yeah, both these are primary. If, however, you want to make an IUPAC name and it's not primary, you have to use the letter N instead of a number to locate those extra groups of carbons attached to the nitrogen. Okay, so here's our examples. We're assigning an IUPAC name, right? So this common name was isopropyl methylamine, but the IUPAC name is, well, find the longest chain. Let's rewrite this. Put an H in there too. Okay, so I drew this molecule out. There's an isopropyl group on the left. Yep. An NH, got it. And a methyl, yeah, got it. Okay. IUPAC names start with find the longest chain with the most important functional group. That's a chain of 3. Here's the parent. Give it a name. Well, that's propane. Drop the E and add amine. There's the parent name. Number of the parent. Well, it can either be 1, 2, 3, or down here 1, 2, 3. Either way, nitrogen's attached to carbon 2. So you put the 2 here or in front of the suffix, your choice. What haven't we identified? 2-propanamine identified everything on the left side, including the nitrogen. We haven't talked about this methyl group. It's not on the chain of 3, it's attached to the nitrogen. So you have to say, hey, there's a methyl group, not on carbon 1 or carbon 3 or 2, it's on the nitrogen. And poor planning on my part, poor use of the screen. Sorry, it's getting a little crowded here. There we go. This molecule's IUPAC name is N-methyl 2-propanamine. What do we got here? We got a mess. Let's go down here at the end of the screen. I'll rewrite this molecule here, and then it gives us the answer. Let's see if we can get to that answer. Oh, and look at that. I got more stuff down here. Okay, we can put the name right over here. Okay, so step 1, step 0. Let's draw the skeletal drawing of this. There's isopropyl group over here, nitrogen, and then 2 carbons, 2 CH2 groups. So maybe 1 carbon here, second one here, and it ends with an alcohol group. All right, let's give this an IUPAC name. Step 1, find the longest chain with the most important functional group. Who's more important, amine or alcohol? The alcohol. So this carbon must be part of the parent. And the longest chain with this carbon is 2 carbons long. Step 2 is name a 2-carbon chain. That's ethane. Give it the right suffix, the alcohol suffix, ol. Step 3 is the number of chain. Get to the most important group as fast as you can. Well, the alcohol is attached to carbon 1 of ethanol. Here's 2. Chain is now numbered. Okay, step 4 and 5 for the IUPAC rules. Walk down the chain, name the extra groups. Okay, on carbon 1, there's the alcohol group. Put the 1 there to identify the location of the alcohol. 2, and I know that's actually redundant, right? If you have a chain of 2, where's the most important group? It has to be on carbon 1. Can't be on carbon 2. But I'm gonna put the 1 in there anyways, just to clarify. On carbon 2, there's a nitrogen, an amine. Well, you're not gonna use the amine suffix, you use the amino prefix. Ooh. Yeah, that's right. Amino, and then let's think of something else. Sorry, distractions. Okay, attached to carbon 2 is the amino group. Hey, the name so far, 2 amino, that's this nitrogen, 1 ethanol, that's these 2 carbons, that alcohol. They've all been identified, but we haven't talked about the isopropyl group. So again, you're gonna throw that in the front, and isopropyl. 2 amino, 1 ethanol. And this is what I got distracted by. The alphabetical order here. I know I got it in this order, and that was my gut feeling. I think if a student gave me, it's not gonna fit. Here we go. Gave me alphabetical orders, I think I have to give you full credit. And as I'm drawing this, writing this out, I'm thinking this might actually be the IUPAC name. Didn't I say earlier that I'm gonna be very lenient on grading the names because there's so many variations? Yeah, I'm sure there's a set rule, and I apologize, I should have looked it up. I'm thinking it might be this one, the IUPAC standardized name, just because alphabetical order. But I could be wrong. It might be an exception. Say, hey, the N's out. Anyways, let's not go there. Construct the name as best you can. Either one's very logical. I'm going to assign full credit to either one. Okay, so we see an example of amino. Definitely saw one with amine. We're using the N. Oh yeah, we've used the letter N before. That's what this stuff is down here. We've seen the N when we talked about aromatic compounds. We put an amine on benzene. The IUPAC name was aniline. And if you start substituting these hydrogens with alkyl groups, you just name the alkyl groups and identify their locations with the letter N. So NN-dimethyl aniline and 2,3-dimethyl aniline is where the methyl groups are attached to carbon. So you've seen it before, right? Change the 2 and 3 to NN, and now the methyl groups are stuck on nitrogen. Did the same thing with amides, right? So find the longest chain with the most important functional group. That's the pi bond on oxygen. This carbon is part of the parent. 4 carbons long is butane. Name of the most important group is amide. That happens to be the suffix 2. So this is butanamide. Hey, we haven't identified the 2 ethyl groups. They're not on the parent chain, carbons 1 through 4. They're on nitrogen. So yeah, we call this NN-diethyl. Squeeze, there shouldn't be a space here. Butanamide. We've used the N locator before. Pause the video if you want to know some fun facts here. Enough about naming. Cool. All righty, we got classifying out of the way. Excellent. Did I get all the points there? I did. Good. All right. All right, we're going to end this video with 2 major review topics. So you've seen all the new stuff for this video. If you want to tackle the homework, you can. We're going to go over order of basicity because we mentioned amines are bases. So how they rank among other bases that we know about. Definitely. If you haven't seen that video yet on the order of basicity, you got to watch it. It's so important. Here's the main points, or some of the main points of that video. If in organic chemistry, you had to look at these molecules and say, who's the strongest base? Well, the order of basicity would tell you that go to the periodic table, step 1, top right corner, look at the nonmetals C, N, O, and F, put in a space there and insert your triple bond. Now make them all anions with a lone pair. And you have now ranked the bases crudely based on electronegativity. The most electronegative is fluorine. It likes to be negative, making it the weakest base. It's like, I'm cool with this negative charge. Leave me alone, H+. Whereas carbon's like, freaking out. Why am I negative? I am not electronegative. I can't deal with this. Why? Life is just too hard. Okay, calm down, carbon. Here's a nice proton for you. Have an H+. Oh, thank you very much. I'm gonna go snag that as fast as I can. I will rip that off of a nitrogen atom or a hydrogen or an oxygen if I need to, because I need that H+ more than you do, which is true. Carbon's less electronegative. It's more basic and will pull hydrogen off the other atoms if they have a hydrogen. Okay, the next criteria after, well, let's see, how far does that get down this list? So here's the answer. Carbon with a negative charge is first, nitrogen negative charge is second, triple bond is third, oxygen is fourth, fluoride or chloride is at the bottom. So the only ones we're missing from this ranking here are these 2. Nitrogen when it doesn't have a negative charge. Sadly, I don't got a nice little way to remember that. You're just gonna have to know it goes here. On the other hand, use your general chemistry experience. Back in Gen Chem, we called ammonia a weak base. And you called sodium hydroxide a strong base. So don't forget that part, because now if you remember this, you can now rank them, right? Hydroxide ion was a strong base in Gen Chem. Ammonia was a weak base. Oh yeah, hydroxide's more basic than ammonia. So neutral nitrogen, with or without carbon, that's the neutral nitrogen with the lone pair, it ranks about the same. More on that in a minute. It's definitely a weaker base than hydroxide ion and stronger base than chloride or fluoride. Let's see, the other one we got in here, what's going on with this negative oxygen? Shouldn't it be right here? No, there's a pi bond next door. It's resonance stabilized. So when we're ranking our bases, order of basicity, the second criterion is look for resonance. It stabilizes bases. So this negative oxygen is stabilized by resonance. You can draw the resonance structure, where sometimes the pi bond moves down here and this oxygen negative. And now this oxygen gets a break. It's neutral, nice and happy with 2 bonds. And this one's like, I'm not too happy here. Here, oxygen, take it back. We'll share the responsibility of carrying this negative charge, but we're electronegative. It's not too bad. It's better than fluoride. At least that's how an organic chemistry would rank it. But I wonder if the KB back in Gen Chem, how that ranked with fluoride. I think it was pretty close. Anyways, put the amines and resonance stabilized negative oxygen and the order basicity right here in between unstabilized oxygen and fluoride. Cool. What else do we need to know in terms of review? Oh, we can rank the bases this way, and then we can use that knowledge to rank acids that are connected. So we just took care of how to rank these bases. What about these molecules over here? Who's the strongest acid? Well, just remember opposites. Whoever's the strongest base up here now becomes the weakest over here. Whoever's the weakest base now becomes the strongest acid. Chloride was weakest base, and the reason for that, back up. The reason why HCl is such a powerful acid is because when it reacts as an acid, donate your H+, that's acting as an acid, it turns into a very stable molecule. It's not even basic. Chloride ions do not change the pH of water. Add all the salt you want, the pH will remain pH 7. Sodium chloride, chloride ions, not a base. Doesn't grab H+. Yeah, it doesn't want it. So if it had it, get rid of it. Strong acid. Go the other direction, methane. Methane's an acid? No, it's not. But if you force it to be, it's going to be really upset. Carbon's really happy with those 4 bonds. It's got a crazy pK value. It is very much not an acid, but if you force it and becomes this anion, it's freaking out. It's one of the strongest bases known. It wants its hydrogen back. So just remember opposites, right? First rank by bases. If you have to do the acids, flip the order. Cool. Let's rank these, right? I said we come back to this idea. Okay, so nitrogen is weak base, CN, triple bond, negative charge O, and then the ammonia would be right here, right before fluoride ion. So it ranks really low. And that's where all that's where all 4 of these would go, right in between negative oxygen, negative fluorine. But some of you are asking, well, are they exactly the same base strength, or is there some differences? Turns out there is a little difference. Secondary bases are the strongest among these. It's still not that much more basic. And the rationale is it has 2 sets of carbons to donate electrons. No. Where is it? It's somewhere else in this key concept, so I thought I'd go get it, but no, let's not go back there. Instead, alkyl groups make bases more basic. We should just go back to the order of basicity. That's step 3. If you're trying to rank your bases, use electronegativity first, then resonance to break any ties. If you still have ties, then look at orthopara versus meta-directing groups. Back when we talked about benzene chemistry, meta-directors deactivated the benzene ring. Turns out the reason that, or the way they do that is meta-directors have a positive charge on the atom attached to the ring. That positive charge attracts the pi electrons away from the benzene ring towards the meta-director. And now those pi electrons don't want to do a reaction. Orthopara directors activate. they pump in electron density. They pump in some more electrons and make the pi electrons want to jump out and react. Make the benzene ring more electron rich. It adds electrons. So now, if you add an ortho-para directing group to a base, it does the same thing. The ortho-para director wants to activate, wants to add electrons, make the lone pair of the base more reactive, more willing to jump out and do a reaction. So 2 carbons are better than 1. And then I have to go back and look at the pK values. It might be better than that. Turns out, though, there's some sterics, some crowding. That's how I rationalize it. This is about as basic as the primary, as I remember. Again, this is for the chem majors. For some reason, if you need to rank the amines, just remember the secondary one's more basic. And then it might depend on what actual groups are here. The influence of basicity a little bit. As I remember, the pK of all of these are around 9. And it's 9 point something. Like, I'm just going to throw numbers out. Maybe this is 9.4, and these are like 9.2, 9.2, and that is that 9. I don't know what they are. But anyways, it's a small variation in the pK value. So there's a small difference in their base strength. Secondary, remember, is the strongest of these 4, and that's it. That's all I really need you to know. On the exam, I'm not going to ask you to rank these. But chem majors, you should at least be aware of that. But the whole class should know, where should we rank the quaternary amine? How basic is this? Well, what is a base? It's an H+ acceptor. So how do these bases accept an H+? They use their lone pair to go grab one. They make a bond to H+. They need a lone pair. 84th degree nitrogen, are you a base? Heck no, there's no lone pair. Oh yeah, Lewis bases. Remember, Lewis base is an electron pair donor. This nitrogen doesn't have a lone pair. It can't donate a lone pair it doesn't have. It is not a base. Not basic. Just like the chloride ion. Not basic. Quaternary amines, not basic. They can't act as a base. Chemically impossible. Okay. Just make sure we're on the, we got the idea here. Let's tackle another example. Which one's more basic? Well, they're both primary. Primary amines. Aren't they the same? You got one alkane group, one set of carbons. Wait, there's some pi bonds here. Pi bonds can do resonance. Well, this lone pair is not part of the aromatic ring. Well, you can still draw resonance structures with this lone pair. So here you go. We have the lone pair, create a pi bond and bump this pi bond up to make a lone pair in carbon. Not very nice. Carbon doesn't like that negative charge, but it can keep going around the ring. And so you can actually draw, well, these two are the same. You can draw 4 resonance structures, one of which nitrogen has a lone pair. In the other resonance structures, is nitrogen a base? This nitrogen in this form is not basic. Ooh, my goodness, that carbon is though, but this nitrogen is not. So some fraction of time, the nitrogen is only basic in this form, capital I, but not in these 2 forms, compared to cyclohexylamine, there's a common name, or cyclohexanamine, IUPAC name. This lone pair is always on here. So the lone pair is always available to attack an H+, donate, be an electron pair donor. This one's more basic. Or we could have used our order basicity, right? Go back to order basicity. First, rank these 2 based on electronegativity. Well, the lone pair is both on nitrogen. That's a tie. Okay, then go after resonance. Oh, nitrogen's next door to a pi bond. This one has resonance. Resonance stabilizes, makes it less basic. Meaning the other one, without resonance, must be more basic. Sweet. Yay, order basicity. Oh, here's what I was thinking, orthopara versus meta-directing groups. Just for a little satisfaction, hey, we got some data. So if we look at aniline, lone pair, benzene ring, and we put something out here, Y is not, ooh, maybe it is. The Y group, I think it is on the periodic table, is that yttrium? There should be some A group, something attached to the benzene ring will adjust the pKa value. Oh wait, pKa, A stands for acid. That's this thing. Here's the acidic group. So having the A group, this extra group, whatever, attached to nitrogen was positively charged with a hydrogen, it can donate that hydrogen away and reform the neutral nitrogen. How willing is it to do that? Well, pKa is sort of like pH. They're not the same value, but they follow the same trend. Lower means stronger acid, right? A lower pH means you have a stronger acid. And the same trend for pKa. The lower the pKa, the stronger the acid. And the higher pKa, well, it's like higher pH, it's more basic. Wait, in terms of acid strength, it's a weaker acid. Okay, so how did the groups do? Well, if you have another amine out here or an ether out here attached to the ring, this is not very acidic. Carbon, not too acidic. The halides, a little more acidic. Meta-directors, much more acidic. Oh, look at this. How do we rank the orthopara directing groups? We got no, carbons, and there's our 0-point halides, and then everything else a meta-director. Amines and alcohols are the strongest activating group. Amides and ethers are strong activating groups. Carbon, activating. Halides, weakly deactivating. Meta-directors, much less so. More deactivating. And it's following the base strength. Or the acid strength, right? How basic are these molecules when they have these groups? Flip your pK, was the strongest acid, now it's the weakest base. The weaker acid, now your strongest base. Yeah, the strong activating groups are activating the bases. Okay, so we're just reviewing order basicity. Nice set of data here. I like that. Enough said. Ooh, not enough said. Okay, we got one more form of nitrogen. Here. There's an amine. Here's an amide. Which one's the stronger base? The amine is. Amides are not basic at all. Okay, that's something you just have to remember. Nitrogen has a lone pair. Why is that not a base? One way to explain it is it's resonance stabilized. Right next door to nitrogen lone pair, there is a pi bond. So you can draw a resonance structure. Let's see, there's two lone pairs here. This lone pair can fall down and create a double bond. That gives the nitrogen 4 bonds plus 1 charge. Pi bond moves up onto oxygen, creates a new lone pair that has a formal charge of -1. This resonance structure has charges. It's not as stable as something with neutral charges. So this is not a strong contributor. It's not a very strong resonance structure, but it helps explain, hey, nitrogen, you feel like being basic? I don't have a lone pair. Can't be a base. The other way you can remember that amides are not bases is if we go back to unit 3 and talk about acid catalyzed hydrolysis of amides. So let's hydrolyze this with H+. Okay, what's the mechanism? Well, step 1 for all the carboxylic acid derivatives is lone pair on the oxygen grabs an H+, and then we go on forward in the mechanism. But wait, nitrogen had a lone pair. Why didn't it grab the H+? Because amides are not basic. That's another way to remember. Just remember, hey, if the amide is going to be a base at all, It's not the nitrogen here, it's the oxygen. Weird, but maybe this is a better explanation. The resonance structure says, ooh, negative oxygen. Yeah, let's go pick up an H+. Positive nitrogen, no lone pair. Positive hydrogen, positive nitrogen, they're going to repel. This part's not basic at all. Okay, that was the first major review topic, basicity of amines. Second review topic is, how do you make these things? In our next video, we'll talk about new reactions, new and improved methods of making amines. But we got some trusty old methods. We should keep an eye on those, use those when they become useful. So I should have did this in order. I will do this in order. The first one is an SN2 reaction. I think this is the first way and the most popular way, I'll admit, of making amines. Start with a primary or secondary halide and add ammonia. Ammonia is a good nucleophile, weak base. Does an SN2 reaction. Sulfur and nitrogen are good nucleophiles. And quick mechanism, right? One step, two arrows. If you're drawing the mechanism, which looks like I am. The lone pair kicks this out. Br minus leaves. Then you need to neutralize this, adding S. Then you want to add S. Add the base, or you have an excess of amine. I don't know. Excess ammonia, rather. So ammonia molecule will pick up this extra hydrogen and make the product, which is what we're trying to do. We're trying to make an amine, synthesize an amine. Let's go to the bottom of this page where we can talk about some limitations. So next video I mentioned, we're gonna have some new ways of making amines. And here's the primary reason why. SN2 is great, makes a lot of fun molecules very easily. One mechanism, one step, two arrows. But after you do an SN2 reaction, and here's the neutralizing with base, you make a primary amine. This primary amine is also a good nucleophile, and it can repeat the reaction, which is great if you didn't want the primary amine. It could do a second SN2 reaction and make it secondary. But what if you want the primary amine? You added too much alkyl halide, then your major product will be secondary. The secondary amine still has a lone pair. It's still a good nucleophile. Secondary amines also can do SN2 reactions, and now they're tertiary. The tertiary amine still has a lone pair. So yeah, tertiary amines can also do SN2 reactions, and it becomes a quaternary amine. And then now finally it stops the SN2 reactions. There's no more lone pairs. If you go into lab and do a 1 molar to 1 molar ratio of primary alkyl halide and ammonia, or you add one equivalent, you don't get a high yield of the primary amine. Well, it is the major product, but only 45%. A 1-to-1 ratio will also create some secondary amine. The math isn't working out here. I have to go back and find the source, right? Because we have one alkane chain, and now we have two. The math isn't adding up. I think we need a lot more of these. Wow, they're actually using less. They're using an excess of this molecule. They're trying to make it go just the primary amine. So using more than one equivalent of alkyl halide. The limiting reagent is ammonia using an excess of alkyl halide, and we're hoping it'll just react one time. In the case, and in the lab, yeah, that only happens 45% of the time. But 43% of the time, that darn product is going to react again with the excess. Oh, excess. Dennis, you're not on your game today. If you add too much, it's going to push it and get more of these. And then you actually can make the trace amounts over here. No, I think I'm bad again. If you reverse it, no, you do want to reverse it. if you had more ammonia, you'd run out of the alkyl halide. That would increase your product of the primary amine. I have to go back and look at this reference. Okay, I'm probably messed it up big time, but here's the main point. All the amines, primary, secondary, and tertiary, are good nucleophiles. So it's difficult, we'll just say that, it's difficult to have a high yield of primary amine if that's what you're going after. Using an SN2 reaction and starting with ammonia, you're not going to get a high yield. You're going to get moderate yields, and they'll be contaminated with the other higher degree amines. It calls for better methods of synthesizing amines. That's the bottom line. However, on a synthesis problem, you can still use the SN2 reaction to make your amines. At least on my exams. Cool. So what are some better ways of making amines? Well, there's two ways that jump right out at me. One is starting with a nitrile. And you can reduce it with the strong reducing agent, lithium aluminum hydride. It's got all these H's, so add a whole bunch of H's. Well, that's interesting. There's 4 of them. And you get all 4 adding. Okay, cool. And here we made a primary. That's what you get out of reacting nitriles with lithium aluminum hydride. Lithium aluminum hydride. You can also get an amine by reducing amines. Same reagent, lithium aluminum hydride. Cool. Oh, this one's nicer though. What degree is this amide? Talk to the nitrogen. Hey, nitrogen, how many carbons are you attached to? Just one, your primary. Oh, good. So you can make a primary amine. If you started with a secondary or a tertiary amide, and reduce it with lithium aluminum hydride, you get the same degree amine as you did amide, right? So, hey, amide, what degree are you now? Nitrogen says, I'm attached to 1, 2, 3 carbons directly. I'm a tertiary amide. After lithium aluminum hydride attacks, the double bond O goes away, and you keep all your carbons, and you get a tertiary amine. Very nice. Cool. Some other ways of making amines that you are still going to be relevant in Unit 4. If you have the nitro group on benzene, you can reduce that in a number of ways. 2 reactions we already studied is 1, you can use hydrogen gas and palladium. The problem though is if you have other functional groups, they could also react. So you take the nitro group and make it an amine, aniline in this case, but your alkene will change to an alkane. So to prevent that, you might say, okay, let's use that iron with acid followed by base to do the same thing. And it turns out this form of reduction doesn't attack the alkene. So the alkene survives, but the nitro group reacts. Cool. And then today, let's add another variation. This one's really common. Iron and the acid work really well. But what I've seen lately is a lot more tin chloride, and it might be a solubility issue. Maybe the metallic metal reacting with the acid is too polar, so they use tin chloride. I know SN is 10 on the periodic table. Under acidic media, treat it with base. Afterwards, and does the same thing. It only attacks the nitro group, making it an NH2 group. Other groups left alone. I think we found our stopping point. Cool. I'll see you in the next video.